my screen.
What was it?
Oh no, I'm just drawing this shape, the pentagon shape. And do we know what the angles of the pentagon are? Let's see. All added up has to be 540. So each one should be what? 108?
Yes, 108.
Oh, okay, 108. 108. 108. 108. And then, well, might as well draw the hexagon too while we're at it.
It's 90. It should be 90, yes?
Huh?
It should be 90 for hexagon?
This one, the angle should be 120 each one.
The total is 720, yeah.
Yeah, the total was 720.
120, yes.
120, yeah. Okay, so let's say you have a kind of, this would be more like an atom, maybe not so much an atom, I mean a molecule in a pentagon shape or a hexagon shape. So let's say just for easiness, this is let's say this is 1 nanocoulomb. 1 nanocoulomb. 2 nanocoulombs. -1 nanocoulomb. Okay. -3 nanocoulomb. And then let's make the Q. Then let's make the distance here 1 nanometer. More like a molecule size. Very small. Well, actually, that's very, very small. It's almost like atomic size. I guess we could make more realistic. We could say micrometer. Micrometer. 1 micrometer. So let's say that all the legs are 1 micrometer. So we could say, what's the voltage in the center? What is V total in the center? So we could do the same thing with the hexagon. Do it 6 charges and give the distances of the legs, you know. You could keep going to octagon. What was a nice shape? Nanogon, right? Nanogon, decagon, right? So you could say, what is the voltage at the center? And what is the potential energy? What is the potential energy of this molecule? Okay, so the voltage at the center is going to be easier. It's just they all add up, right? So as long as we know these distances, the distance is all going to be the same, right? So if this is 1 micrometer, what's that distance going to be? So I guess you're cutting this in half, right? If you take one of those triangles, this is 1 micrometer. So if I want to know if this is 54, and this is 54. So I'm focusing on this triangle now. It's 54, 54. And then if I want to know this distance, what would that be? I guess we could say, so this is 1 micrometer. This from here to here is 0.5 micrometer. Right, so cosine of 54 is 0.5 over d. Right, right? So if you view it this way, cosine of 54 is the adjacent over the hypotenuse, right? So cosine of 54 is 0.5 micrometer over d. Okay, that's how we can find the distance. So now the distance is going to be 0.5 divided by cosine 54. 0.5 divided by 54 cosine. Okay, so d is going to be 0.85065 micrometer. Okay, so then what's going to be the total voltage? Well, the voltages will just add up. So V total, and the distances are all the same. So it's just K over R, and the R's are all the same, right? And then Q1 plus Q2 plus Q3 plus Q4. Oh boy, do I love voltage, right? You don't have to worry about direction, right? Just add them all up. As long as the distance is the same, so 9 times 10 to the 9th. The R is the distance that we got, right? So KQ, I'm using KQ over R, and then R is the 0.85065 times 10 to the minus 6. Right? And then the Q's. So 1, that's 2, -3. Well, actually, you could say this and this cancels. So this and this cancels. Oh, actually, the total charge is 0. Yeah, so 1, 1. This cancels. 2 and 1 is 3. -3. Oh, I didn't mean for it necessarily to be like that. So we got lucky. 3 and -3. Oh yeah, so the total charge is just 0. So that would be cancel. I could change it in a minute and say what would it have been if it wasn't like that. But is that going to make the potential energy necessarily 0? If the volt, that's a different question, right? Let's see if the total charge is 0. So the total voltage, the voltage that it creates in the center is 0. But that's only the voltage that it creates at the center, which is 0. V total at the center. So it's 0 volts, literally. This is one of the ones where if it was on the test, and then one of the choices was 0, probably no one would put it. They wouldn't believe that the answer could be that. Okay, how about the potential energy? U total. So remember, each charge will have potential energy with all the other ones. So you have to kind of keep tabs. This guy has potential energy with this and this. So you kind of can start with this, like number 1. So the potential energy of number 1, and then maybe number 2, potential energy of number 2, then number 3, potential energy of number 3, plus potential energy of number 4. I think that's it. Okay. So now, number 1 has potential energy. So number 1 has potential energy with 1n2, 1n3, this one, and 1n4. So this one I labeled 4, right? Hold on. 1, 2, 3. I labeled this 4. I thought I labeled it. I guess I forgot. So this is my labeling. So 1, 2, 3, 4. So number 1 has potential energy with 2, with 3, with 4, and with 5. Okay. Number 2 has potential energy with 1, but you've already accounted for that, you see. So you don't double count it. So then you say number 2 has potential energy with 3, with 4, with 5, with, that's it. So it's kind of like, imagine you get a group of 5 friends and you say, how strong is that friendship? You know, it's kind of like that, the human analogy of that. Then you say, this guy has a friendship with that guy, so let's see the strength of that. This guy has a friendship with that, let's see the strength of that. Let's see the strength of that. But then this guy maybe doesn't like this guy, you know. So being a negative charge and a positive charge means you like that person, and being a negative and a negative means you don't like each other, or positive and positive. You see. So that would be the total human analogy of this. So then you have to account for all the friendships to say how that group's strength, friendship strength is, you see. So of course you probably want more opposite charges to each other, you know. You want some positives, you want some negatives, right? Okay, so then you want here U3 has with 4, U3 has with 5, right? And then U4, so this is the potential energy that 1 has, 2, 3, then 4. So of course you're saying, well, how about the potential energy with 5? Well, we've already counted with all the friendships that 5 has with everybody else, you see. So it really doesn't matter which one you label 1, 2, 3, 4, 5, as long as you count for all of this. Okay. So then 1 with 2, what's that gonna be? 9 times 10 to the 9th. So then 1 with 2, so negative 1 times 10 to the minus 9, negative 3 times 10 to the minus 9, over that distance, 1 times 10 to the minus 6. Mm-hmm. You know, I'm going to try to get this whole thing in here so you can see the original picture. It's hard. Okay, that's better. Okay, so then you have, let's not write all the 9s and stuff, so maybe this one is redundant. And then the power of the 10, this is going to come out what? 10 to the minus 9, 10 to the minus 6, so it's going to come out 10 to the minus 3. So we know all of them are going to come out 10 to the minus 3, so the answer is going to be millijoules at the end. Millijoules, because they're all going to be the same order of the power 10, right? So then U13 is going to be 9, negative 1, 1, over, what's that distance? Have we calculated that here? No, this is 1, 1. So we have to do that, right? This distance. The minute ago, we calculated this distance to the center. So what would this guy be? So if it's 1, 1, what would this distance be? This is a 108-degree angle. Oops, my pen is dying. $108. So then what would this distance be? I guess the easier way would be to just break this in half, right? because it's isosceles, and to say this is just 54, and then to say this is d over 2, right? So sine of 54, this is a 90-degree angle, sine of 54 is d over 2 over 1. Okay, so then that's d. D is 54 sine times 2. So D is equal to 1.618 micrometers. Okay, so then this distance is going to be 1.618. Okay, so we're still on U1, U13. So let's expand this here. So we did U13, then U14, at least the distance is the same as this guy, right? Because it's this one right here. So yeah, so then that, what will that be? Negative 1 and 1 again. Well, it's the same thing. Negative 1 and 1, negative 1 and 1. So we could just double this. Okay, then we got negative 1 and 2. Negative 1 and 2 and 9 over that distance, which is 1. Okay, so that one is so far this guy. So plus U23, 2 with 3 is going to be 9, negative 3, 1 over 1, plus 9, negative 3, and 1 over what? That distance, where was it? 1.618. Okay, and then this with this, 9, negative 3, and 2, right, over 1.618. Now it's getting easier because we have less energies to account for. Okay, U34 is with this, so 9, 1, 1 over 1. This with this, 9, 1, 2 over 1.618. And then that's it. That was just 2 of them. It's this Y. Oh, you guys can't see it, huh? Okay, so this one is these two, U34. And then the final one, U45, is going to be what? This with this. Oops. Just trying to get the whole page. So 1 with the 2, right? U45, 1 with the 2. So 9, 1, 2 over 1. Woo. So it's a matter of just accounting everything that's possible for energy. Okay, so don't worry about powers of 10, they're going to come out millijoules. So 9 times, this is going to be 3, so that's 27. This is going to be negative 18 over 1.618. This is going to be negative 18. This is going to be negative 27. This is going to be negative 27 over 1.618. And let's see. And this is going to be, this is the largest one. This is going to be negative 54 over 1.618. And then this one is going to be positive 9, positive 18 over 1.618, and then positive 18 right here. So one little mistake can throw the whole answer off, right? If I forget something. So then here, oh, okay, there's some cancellations. That's good. Positive 18 cancels the negative 18. 27, oh, cancels the negative 27. This guy cancels this one. Oh, wow, I like that. What's left? That's it. So 9 minus, and then 27 and 54 is what? 81 minus 81 over 1.618 millijoules. That's going to be the answer. So as you can see, just because the total charge of the system was, that's kind of weird, right? Yeah, the total charge of the system was 0. The net charge of the molecule, at least from that point of view, was 0, but they still had energy. The molecule still had energy. Yeah, I'm looking at it. It's kind of interesting that it worked out that way. 2, 4, yeah. 9 minus 81 divided by 1.618. Wow. Negative 41.606 millijoules is the potential energy. So that's how much work it's required to remove all those charges, to separate them out to infinity. Looking at the numbers, can you see here, how is it that even though the net charge is 0, but then the potential energy is negative? In other words, how can you explain that conceptually? What's happening here? Let me draw it like this. These three are kind of say, so even though the total charge is 0, but it's not symmetrical. So you have kind of like 1 nanocoulomb, 1 nanocoulomb, 2, that's 4. And then you have negative 4 here, but the negative charge is more concentrated. In other words, the negative charge is concentrated into 2 charges, and then the positive charges are concentrated into 3. You see, they're kind of concentrated more in smaller increments, right? And then each of those positives are bound to those negatives. They like being with them. So this guy likes being with that. This guy likes being with that, right? You see, and then these two like being together. These two like being together. And these two it's weak, their charges are weak, so they have less say. in that friendship group. These two get along with those guys, but they have more say, kind of. 3 and a 1, especially the 3, you know. So this is the culprit right here. This guy helps bring the group together. In other words, the power here, even though it's -4 and this is also 4, but the power is concentrated in one person. I guess, well, I don't know. Is there like a big life lesson in that? I guess so, right? You can always find life lessons in science.